Very good. So let's continue. So in this case, we have the truth table of A XOR with B. And the corresponding decision tree for this can be drawn like this, yeah, where A, in this case, if false and true, then the node that the leaf node that goes with it is B. So if A is false, and in this case compared with B, and if B is false, and then the result is false. So we're just following the truth table of the XOR. And the same thing, if A is false and B is true, then the result is true. Okay. So if you follow through the branches, then you can get the final result of the XOR table, of the XOR, yeah, logic. So again, if your A is true, then the same thing you can follow, and then this is the result. Well, that's easy. That's easy because it's just two layers, and they were just XOR logic. But if you have many statements, like for example, uh, in this case here, a logic, if you want to have a Boolean logic for this particular more complicated problem, then uh, it will be very complicated to come out with this Boolean logic for such a complicated problem. And so there's a way for us, instead of using Boolean logic only on the decision tree, we want to build a decision tree, in which case that will give us a much better a much better uh, uh, predicting ability, yeah, because not all trees are equal. That is the idea of a decision tree. For example, here, let's look at the simple example of the XOR. So why in this case A is our root node when B can also be a root node, isn't it? Yeah. So, but then is it because A is XOR with B? Is that not commutative? Okay. Maybe it is not commutative. I cannot remember. Is it commutative? That means B XOR of A is equivalent to A XOR of B. I think they are commutative. Okay. If they're commutative, then it doesn't matter whether A is in the root node or B is in the root node. Okay. But in our discussion here, we'll further down the road, we will discuss on how which node are better to choose to be the first layer and second layer and so on, depending on what we call an entropy computation. But that will come later in the discussion. But for now, what I want you to remember that there are many ways of constructing the decision trees. Okay, and then not two decision trees are equal. Not all decision trees come in many forms, as long as you can come out with a particular decision. And some decision trees are much better constructed than the others to have a better prediction ability. Okay, so let's continue. So are all decision trees equal? Many trees can represent the same concept, but not all trees have the same size. Okay, not just the same size, but not all trees can have uh, uh, a better predictive ability as you go down the layers, as we can see later in our discussions. So, for example, in this case, a Boolean decision of Boolean decision tree of A uh, and with B, and not A, or this is and, right? Not A and with C, and then in these two cases you or those two cases, yeah. So A and B. So in words, A and with B, and you or it with not A and C. So how do you build the decision trees in this case? So now you can choose, if you choose A as the root layer or the root node, okay, then you have two other layers, B and C. Okay, you can have this A if A is true, and then you have the leaf node B, and then now you can choose between A, true or false, and then you can have a decision of positive or negative or true or false. Okay, and then when A is false, you have a leaf node of C, and you have true or false decision I mean, true or false parameter or criteria for C, then you have an output of false or true, I mean, true or false, positive or negative. So in this case, this simple tree represents this idea, okay, the logic equation on top, as well as this, the other decision tree that is big. In this case, this is more layers. It has 1, 2, and 3 layers, where the last layer is the leaf. So now you have a much bigger tree, but the decision will become the same. So of course you want this tree because it's much simpler. If this is in the computer, if you run it in the computer, this one will take a faster computational time, and then while this one will take longer, of course, because there are many branches that will go through. Yeah, and if it's a very complicated decision tree, then of course you want to have a much simpler representation. So how do you come out with this one, with a better one compared to this one? Well, you have to try many different at this point, you have to try many different combinations. So it just so happened that when you choose A, okay, in this case here, when A is true, there should be two other cases here. It should be, should compare between uh, C, a false, an A that is false. You should also compare it with a B. For example, here, why is it that it is a C immediately and there's no B? It should be A and then layer B here for true and B here for false. And then here there should be C, another layer for C. Yeah, so that you can make a decision. But in this case, why? That for A, for the true A, when A is true, you only compare it with B. And then in this case, when A is false, you only compare it with C. Okay, compared to here, B, you have true or false B, then you compare it with C. The true B compared it with C, and the false B you compare it with C. And then later you compare the false C with A. Okay. And then, but then you don't compare the true C with another A and then come out with a decision. Okay. So in this case here, compare C only with this true value of A. And then here you don't compare A here. You come out with a decision. Okay. The reason later I will show you is because it doesn't matter. It won't matter. If you put an A here, okay, if you put an A here, the result will be all negative. Okay. So whether you put the A here, it doesn't matter. You can put the A here, but then it's just a useless computation and you want to save computation. Okay, that is a reason for that. The same thing as here. If you put an A here, okay, to compare with to be compared with C, that is a true C, you put another A here. The result of the leaf here, I want to show you so that you can see it. If you put an A here, and then there is true and false, then the result will be true and true. Okay. So in a sense, it doesn't, it's just an extra computation that you can remove because there's no decision anymore. So this one is omitted. Okay. So in the other case here, if you also want to put an A here instead of the negative, then the same thing. If you compare the true and false of A, in that case, it will always be negative output. Okay. So that's why it is omitted. Okay. So is that the same case as on the other side here? Yes, it is. Because here, if you put a B here, the result will always be false, will always be negative. And so there's no matter you put a B here or you put then the result here will always be false. Okay. There's no point putting more layers. If you put A false with, and then A is false and B is there, it doesn't matter. Okay, you put a B here, it will always be negative. Okay, so that means in this case here, you can, okay, because the complete set of this layer here will be A and B like that. And then you have a C here. And then you have a C here. Then you have a C here. You have a C. And then you compare. Yeah, that's the complete set. But for now, we didn't discuss yet in detail. But as in this case here, you can remove some of them. Okay, you can remove some logic that is not useful, so that in this case here, this one doesn't add value, and so the result can be canceled, so that that branch of A false, and with B, with the B node, does not matter. Okay, so you put a C there, so to compare A with C. Okay, because here also you don't put a C down here, because here it doesn't matter anymore. Okay, if you put a C here, it will always be, whatever is the result here will be positive, and here is positive, and the C here is negative and negative. Okay, so that means this layer here does not matter, because the result is always negative. This C layer here does not matter, because the result is always. So now this one can go away. Okay, we will show in an example later. But for now, we say that some branches are removed because those branches are not necessary. Okay, so in this case now, it is good for you to just note that, you know, uh, there are trees that are doing exactly the same thing, this exactly representing the same concept, but some of them have, much more compact construction compared to others. And of course, the smaller the size is, the smaller the computation. Okay, of course, we prefer this tree that's smaller. Okay, so let's go on to a video. I have this video online. Let's just listen to a video, because it will help you in appreciating the concept, rather than me talking all the time.
Next few minutes, 15 minutes or so, we've been talking about decision trees, sort of in the abstract, without saying too much about the kinds of functions they can actually represent. So for the next few minutes or so, I want to talk a little bit about not just decision trees in the abstract, but exactly how expressive they can be. Is that okay?
Yeah, I think that'd be really helpful.
I think so too. So in fact, I want to look at a set of functions, and in particular, I'm interested in looking at Boolean functions.
Boolean.
So what's your favorite simple Boolean function?
Implication.
What's your other favorite simple Boolean function?
Well, I like nor.
Right. So what I just heard you say is you like and. So let's do that one.
Oh, that's great. That is my favorite.
All right. So in fact, let's do very simple and. So how does and work, right? So you've got two attributes, let's say A and B. And this expression A and B is true when?
When A and B are true, when they're both true at the same time.
Right, exactly. So how would you build a decision tree, given that there are only two attributes, A and B, to represent that function?
Okay, so I'd have a node that's A and B, and if
Nope,
that's
you're not allowed to do that.
oh,
Every node can have at most one attribute.
all right. Well, let's put A in an attribute.
Okay, so here's a little node. Let's call it A.
Okay.
Now what?
And well, I mean, for it to be a node, it needs to have the little two branchy things, true and false.
Okay. All right. So how about true on the left and false on the right?
Sure, as long as you label them. So, all right. So then if A is true, okay, I don't know, but if A is false, then we know that A and B must be false. Doesn't matter what B is. So we can just put
That's
a leaf
correct.
at the under the F.
All right, I like that.
Okay.
What about when A is true?
What is that, an F?
That is an F, and that is a minus sign.
Oh, a minus sign.
false.
I get it. Okay, I thought you were just not done drawing the F yet. Good. All right. So, okay, the true side, then I don't think we know. So I think we need to split on B also.
Okay.
So put a little B under there.
All right, done.
All right, and then true, false, split on B. All right, and so now we've got these two cases. So if B is false, then again, it doesn't matter what A was, but A turns out to be true, but it's still it should be a minus sign underneath that.
Okay.
So it's not, A and B is not true. But if A is true and B is true, then A and B is true. So there should be a plus sign on the left.
That's exactly right.
Woo.
So clearly decision trees, proof by, we just drew it here, can represent the Boolean function and.
Sure. At least on
Right.
two
Now,
inputs.
you said something interesting, Michael. You said it doesn't matter what A is if B is false. So what would happen if I switch A and B around?
That's the same. So if B, okay, so in the beginning we say if B is false, it's false. If B is true, we check A. If A is false, then it's false. But if A is true, then it's true. So it actually still represents exactly the same function, A and B. Oh, because A and B is collaborative. No, commutative. Yes? No? Hello?
It's one of those things. It's commutative.
Commutative.
As opposed to associative?
As opposed to what?
Associative.
Well, I mean, it's that too, but I mean, it's the reason that you could just switch those two things and it didn't make a difference is because they play the same role in the function.
That's true. And in terms of the representation of decision trees, you know, it doesn't really matter which attributes you pick or the order in which you do them. You might get a better tree or a worse tree, a longer tree or a shorter tree, but for something simple like two-valued and, it really just doesn't matter.
Okay.
Kind of neat, huh?
Yeah.
Okay, so that's one. And then let's go to the other. This or. Those are
Hey,
used to
team,
be-
Justin Zeltzer.
Okay, so
here
we can
from
do A and B.
Statistics
So let's
dot
pick
com,
another function.
Where today,
What's
I'm
your other favorite Boolean function of two variables?
Well, if we're doing two attributes, you know, or is the other really nice one.
I like or. So let's see. Do you think now that we've shown that we can do A and B, could we do A or B?
Feel like we could do A or B because there's that nice De Morgan's law relationship between them. But let's just, how about this? Can you erase the tags at the bottom?
Like that?
Oh, yeah, but that's not going to work, is it? So if B and A are both true, so the left branch, then the leaf should be plus.
Yes.
And if B is true and A is false, then the tag should be plus.
Yes.
And if B is false, I want to say false, but we don't know because A could be true and A or B is true if either of the two of them are true.
Okay. So maybe the mistake here is just trying to use exactly the same thing. So let's just erase it.
All right.
And start from scratch. So what would you do starting from scratch?
I'd split on B again.
Okay.
True, false, or false, true. True, false.
True, false.
All right. And now if B is true, we know that A or B is true. So we can put a plus under the left side.
Right.
But if B is false, then we need to split on A.
Okay.
And if A is true, then we're golden. We got the or is true. And if A is false, then it is false.
Very good. And that represents A or B.
That represents the function, the logical function A or B. Yeah.
Right. And what happens if I swap A and B around? Does it still work?
I mean, since they're collaborative or commutative, since they're commutative, I want to say it shouldn't make a difference, but let's just double check that. So if A is true, then the output's true. If A is false and B is true, then the output is true. And if A and B are both false, then the answer is false. Yeah, totally.
Excellent. And you know, if I hadn't erased it, you would see that the two trees actually look very, very much alike.
They're sort of
We just swapped
mirror-ish of
around.
each other.
Yeah, yeah, exactly. They're mirrors of one another.
Okay, we're almost done. Let's stop this one and then let's go to the third one. And just the XOR because that's the table that we discussed. I was shown in my slide.
Okay, let's pick one more Boolean function to do. What function am I thinking of?
XOR is always good.
Let's do XOR. So what does XOR mean? Remind me.
Okay, XOR is exclusive OR, which means it's true if A is true or B is true, but not if they're both true. So it has elements of both or and in it.
Right.
And I think of XOR usually when I'm like playing with light switches in my house. If I have a light that's activated by two different light switches, it's usually an XOR function. If one is up, the light's on. If the other one's up, the light's on. But if they're both up, the light goes back off.
Right. The other thing, when I think of XOR is when people say or. Most of the time when people say or, when they're talking, they mean XOR.
Really?
Yeah, so a lot of times when people say or in English, they really mean XOR. They say, well, do you want to go to the movies or do you want to go swimming? Do you want to eat chicken or do you want to eat fish?
Hmm,
And really they're saying either or.
I see. You want one or the other, but you can't have chicken and fish or go swimming and the movies.
No, those things are not possible to do together.
Got it. Okay.
All right, so how would you do XOR? We still
Well, I
have
would
our two
start with
attributes A
the
and B.
or because it's a lot like or.
So what would you want to do?
Okay, so to do XOR, we can split on A,
Okay,
and there's a true branch and a false branch. And what happened with and or at this point is there was at least one branch where we actually knew the answer at this point. But I don't think that's true
right.
here. So if A is true, the output might be true or false. It depends on B. And if A is false, the output might be false or true. It depends on B. So
that's exactly right. So I guess in both cases, we still have to split on B.
okay, all right. So now it should be relatively easy in the sense that there's a separate leaf for all possible inputs. And so we can just write the XOR function on the bottom. So if A and B are both true, then the output is false because it's exclusive. If A is true and B is false, then it should be true because A is true. If A is false and B is true, then it should be true because B is true. And if A and B are both false, then it should be false.
That's right. And by the way, if you were to think about it a little while, it would probably occur to you that this tree is just another representation of the full truth table.
Ah, very nice.
And in fact, if we wanted to do or again, we could say, well, I was very smart last time, but I could actually write or like this. And then just fill out the values at the bottom. If A is true and B is true, then yes. If A is true and B is false, then yes. If A is false and B is true, then yes. If A is false and B is false, then no. And this is a perfectly legitimate decision tree to represent or, because it basically is just another simple representation of the truth table. But as we pointed out when we did it last time, it's more of a decision tree than we actually need.
I can see that.
Because in particular, we don't actually need this. All right, so this little difference here between writing out the entire...
Okay, so we don't need to listen to those jokes anymore. So as you can see, there's nothing is preventing you from making a full decision tree. As here in the OR tree, if you want to go through the next layer, that is possible, but it is not necessary. So for the XOR table, in this case, you really need to have the full tree to be able to come out with the right decision. Because as you can see, the leaves, the decisions on the leaves are unique for each branch. Okay, so there's no way you can reduce it. Okay, so that's for the simple examples of Boolean decision trees. Okay, so let's continue. How come? Okay. So for example, let's go to one a little bit more complicated example where you come out, we already dealt with this Boolean logic. I think I'm not sure which course you did it, but we are going to use exactly the same logic, Boolean logic equations to come out with a decision tree. Okay, so now again, our inputs in this case are A, B, and C. Yeah. And then we will come out with a phi. Phi is the decision that is based on all these logical relationships between these logic arithmetic or yeah, logic computations. So we AND A and B and then OR it with B and with not C and then OR it with not A and with C. So to do that, we'll just come out with a truth table. So the truth table is this. I'm sure you know about this. So A, all three true and false, and B, we take all the combinations of A and B inputs. Okay. So given this, we will try to compute the each of these items here, or each of the component. So not A and then not C, and then that's it. We use not A and with C, and then we can see the result. and B not with B and with not C and see the results, and A and B and see the results, and then come out with the results of the phi. So from here we can create our decision tree. How? So these are two Boolean decision tree functions that is based on that on those Boolean decision table. Again, how do we do this? So let's go through it one by one. Hey, oh, I thought I computed this. Okay. Anyway, so I thought I had another table that shows each of these. How come it's not? Huh. Okay, let's go through it one by one, just as I promised. So, okay, let's just create another. Let's create a paper for us to write on. Okay, this. Okay, so we have this truth table, and I want us to exercise on how do we make the decision tree out of that truth table. Okay, so let's delete this and delete this. Okay. So again, all we need to do is come out with like this. The nodes will be based on the input parameters. Our input parameters are A, B, and C. Okay. Not this one is not anymore an input parameter. Not A and with C, that's not anymore an input parameter. That is already the relationship. Okay, or the function that is how the inputs are being manipulated. So now we consider our attributes or the parameters A, B, and C. So let's start with A. So if we say we have A, okay, and then we look at the truth table, okay, and then we have true here and false. Okay, maybe just make it like this so that it's easier to see. And then B, uh, true, false, then B, true, false. Well, let's just complete the whole table. Nothing is preventing us from doing that. C, C, and C. Okay, and then come out with true, false, true, false. Okay, time is running out again, but I will just send you a new link. So this true, false, true, false. Okay. So in general, you can just, for a Boolean case, you can just create something like this. Yeah. And then we will just check what happens. Yeah. So A is true. So all of these are the case when A is true. Okay. There. A is true. Okay. And then we look at B being true. Okay. If B is true, so these are the case. And then B is true. And then C is can be true or false. So this case here, in this case here, C is true or false. The result is always true. So in this case here, this is a plus, and that's a plus. Okay. So that means this case does not matter. Okay. This one we can disregard because that does not matter. And then in this case here, what about A and B? If A is true and B is true, so if A is true and B is true, the result is true. So that's positive. Okay. So can we remove a B in this case here? can we remove B? We can remove B if the result of A, if A is true and B, true and false are all true. Okay. So if this is plus over here, we can remove B. But in this case, when B is false, the result is false. So we cannot have this one. So that one we can remove. So that means we need this branch over here. So now let's go to A is true and B is false. So now we are in this case. Okay. And then B is false, and then C is true or false, but then the result is false all the time. So that's negative and that's negative. So that means, again, this case here is not necessary. So we remove this one, and the result here is negative. Okay. So next, let's go to, let's make this one a different color. So this is now the A that is false. Okay. And then we compare it with B that is true. So this is false, and B that is true, and B being true or false. So in this case here, if B is true, C does not matter. So in this case, B is true or false, the result is still true. So this one is still true, and that's true. So this one does not matter. We remove this, and this one is true. Okay. So next, when you have A false and B false, so we are here, and you have your C being true or false, so this one is also true. So if C is true, this one is true, and if C is false, that is false. There. So that is one of your tables, which is in this case, I mean, that is one of your uh, the decision tree. So here, okay, I want to delete annotation. You have a question? Where's annotation here? There. Okay, I want to erase some of them so that we can see it. Let's erase this. As you can see, this decision tree is similar. This is that one. So you have A on top, A and B, and then over here, we remove this, and then for true, it's positive, and false is negative. So this layer is not anymore necessary. And so in this case, if A is false and B is true or false, if B is true, then that's positive. This one is not anymore necessary. And C, you have, okay, that's easy. Okay, so then the question is, what if we want to use instead of choosing B as the next layer, you choose C as the next layer? So will it happen like this? So let's go back there just for exercise. So let's do that. Annotation. So if you want A, let me use A. And then again, okay, and the second, you want C as the second layer. F, I just threw here an F so that it's easier. Same thing as last time. And then T and F. And then T and F. Then you have B in this branch, B in this branch, B in that branch, and B in that branch. Okay. And then again, you have, okay, you have another branch which will be dictated by the output of the truth table. Okay. So let's go through the truth table. So if A is true, so this is all true. And then now C, because we're comparing against C, C is, if C is true, okay, if C is true, this is C is true, and this is C is true, okay. If C is true, then B can be true or false, yeah. So if C is true, here B can be true or false. B is true, and B is false. there. And the output is when B is true, that is true, and false this side, that side, that is false. There. They have unique results, so we have to keep them. Okay. Now let's go to when it is false. So if C is false and C is false, okay, and then B can be true, B can be false. So we have true and false here. What is the result? For B being true, that's positive. And B being false, that's also that's negative. Okay. Again, the outputs are unique, so you have to keep them. Okay. So next we go to the other side. So we go to the other side when you have this false of A, and then you have C being true. So if C being true and C being true, you have B false and true. Okay, so C being true, you have B false and true. Again, you have false and true here. You have false and true. Okay. Then now you have when B is true. Ah, so I changed it. So now when B is true is here. And so this one is true. So that's positive. And then when B is false, this is also true. Oh, is that correct? Yeah, this should not be matter. This should be removed because in this case here, it is not dependent on B, but it is dependent. Okay, if you have true, you have, if this is true, is that correct? If C is, you're taking C true with A being all false and C is true, and then B false and true. But both of them have the same result. So plus, plus. So that means somehow this is plus. So this should be plus all the time, and this one should be removed. Let me check. Okay. Let me not remove it now. Let me just check on the okay, let's just do this because we know that this is not necessary. Okay, and next, if we do C being false, so again, this layer here, I mean this idea here, and B being true and false. Okay, so if that is false, so if B is true, so where is false? This is false, and B being true, so that's true, so that's positive, and again, that's false, and B being false, this is negative. Okay, so that means that this one, only this one is the one that we can eliminate. Okay, and then let's go and check.